Alright, so Assalamualaikum warahmatullahi wabarakatuh. My name is Asmaa Zafirah binti KAMALUZAMAN with metric number 196778. So today I will be presenting the SEL for MTH4205 entitled Proving Process and Example of the books the Cryptanalysis of RSA and its Variants by M. Jason Hynek from page 96 to page 101. Okay, so let us start. Okay, so from page 96, I will be reading the second attack, which is the second attack on RSA with arbitrary public and private exponents, follows the same idea as the first, except that in addition to using the most significant bits of the private exponent, it also uses the most significant bits of the constant k in the key equation. So in particular, we let n be an RSA modulus, which is E equals to n to the power of alpha, be a valid public exponent, and D is equal to n to the power of beta, be its corresponding private exponent defined under modulo phi n. So given D hat such that D minus D hat, modulo of D minus D hat is less than n to the power of delta for some delta is between delta is between 0 to beta, then K hat is given by this equation for some modulo epsilon is less than half, reveals some of the most significant bits of K. So in particular, we notice that modulo of K minus K hat is equal to this. This we get from the above attack. And then we get this from 6.2. And then it equals to this. And then we multiply by each other denominator to get the same denominator like this and plus epsilon. And then we will get this. We will reduce to this, and then we will get this whole equation is less than this, and we label as 6.3. And then from here, since E is less than phi n from the start and the D hat is less than n, it follows that K hat always satisfies modulo K minus K hat is less than this. We substitute E and D hat into this equation and we will get this. We will get this as equation 6.4. Okay, so although beta bounds can be obtained depending on the actual RSA parameters, using knowledge of both D hat and K hat results in a stronger attack for certain sizes of public and private exponents. So the first attack that we use the result is where we for every positive epsilon, there exists an n naught such that for every n is greater than n naught, the following holds. So we let n be an RSA modulus with balanced primes, and then we let E is equal to n to the power of alpha be a valid public exponent, and let D is its corresponding private key. And then given the public key E and N and D hat satisfying this condition, if either of two of these cases, so if one of two conditions is satisfied, so we can factor n, right? One of these two condition 6.5 and condition 6.6, so we can factor n. Okay, so we justify the attack by letting K hat is equal to the CIL function of E D hat minus 1 over n. We notice that the key equation can be written as this, where D naught is equals to D minus D hat, K naught is equal to K minus K hat, and S are the only unknowns. This suggests looking for small roots of the polynomial G, polynomial function G, which is this. Okay, so function G is in z s y z. Okay, since x naught, y naught, and z naught is d naught, k naught, and s is a root of function g over the integers. Defining x equal to this, y equal to this, and z equals to this, we notice that we will get this modulo x naught is equal to x, modulo y naught is equals to y, and modulo z naught is equal to s and z. All right, so when we let gamma is equal to this, the bound for y naught follows from 6.3 using this condition until this condition. With these bounds, we notice that w satisfies this. Right, so it then follows from theorem 2.13 that for sufficiently large n, Copper-Smith method will find two linearly independent polynomials, each algebraically independent with function g with root x naught, y naught, and z naught over the integers, provided that enabling condition for the equation 6.7 for any torque greater than 0 is satisfied. And then we substitute the values of x, y, z, and w. So this enabling condition reduces to this condition, right? When looking at the exponents of n and ignoring all small constants that do not depend on n. So whenever gamma is positive, the left-hand side of this inequality here, left-hand side of this inequality is minimized when torque is given by torque mean equals to this. And then we replace torque with torque mean. It follows that the enabling condition is satisfied when this equals to equation 6.8. So there are two cases to consider. First, we let delta equals to this so that gamma is equals to a plus delta minus 1. And then we're solving for delta using this value of gamma. And then we will get this. Okay, where epsilon is positive has been added to account for ignored constants and lower order terms. For this bound, to ensure that torque mean is the optimal choice of torque, the condition gamma is positive requires that alpha plus delta minus 1 is positive. Also, since torque minimum is positive mass whole, it follows that delta is less than 3 minus 2 alpha over 4. This shows the first bound 6.5 along with all of its additional requirements. Next, the second case where we let delta is less than beta minus half, so that gamma is equals to alpha plus beta minus 3 over 2. And then we solve the equation 6.8 for delta with this value of gamma, and then we will get this equation, we will get this delta, where again epsilon minus epsilon s greater than 0 has been added to account for ignored constant and lower order terms. And then same with the first case, we to ensure top mean is optimal, so we use the condition a plus beta is greater than 3 over 2 to ensure that gamma is greater than 0, and the condition of delta is less than 2 minus alpha minus beta, and then we ensure that top mean is positive, which completes all the additional requirements for the second bound 6.6 in the attack statement. So these two attacks apply for arbitrary public and private exponent sizes. So in practice, however, it is expected that at least one of the exponent will be full size. So we consider these typical cases below. So Firstly, I will be explaining about full-size public exponent. So when the public exponent is full size, there are partial key exposure attack that can break RSA for any size of private exponents, provided enough of the most significant bits of the private exponent are known. So for small private exponent attacks from chapter 5 can be considered partial key exposure attack in which none of the most significant bits of the private exponent are needed. Thus, for private exponent D is less than bit n to the power of 0.25, Wiener's attack can efficiently factor the modulus. For larger private exponent up to about n to the power of 0.2929, Bonnet and Durfee's attack can be used to factor the modulus as well. So for larger private exponents, the best known attacks are the two arbitrary exponent attacks from above. In particular, we let A is approximate to 1 in attacks 6.2 and 6.3, and then we will recover Ernst et al.'s original results, which we restate here. Okay, so attack 6.4, where we let n be RSA modulus with balanced primes. We let E be a valid public exponent and let D is equal to n to the power of beta be its corresponding private exponent under modulo Vn. We were given the public key E and n, and D had satisfying this condition where we use this equation 6.10. And then the modulus can be factored in time polynomial in log n. For attack 6.5, we also use the same lemma, right? We were given the public key and D had satisfying this condition. If either of these two cases is satisfied, then the modulus can be factored in time polynomial in logarithm in log n. Okay, so notice that the bounds for attack 6.4 and 6.5 match when beta is approximate to 0.459. So with attack 6.4 being stronger for smaller private exponent and attack 6.5 being stronger for larger private exponent. Next, I will explain about the full-size private exponent. So when the private exponent is full size, there are partial key exposure attacks that can break RSA for any size of public exponent, provided that enough of the most significant bits of the private exponent are known. So when the public exponent is smaller than n to the power of half, there are several attacks by Bonnet, Durfee, and Frankel. All of these attacks rely on the following results that allow them to essentially know the constant in the key equation. So then we let n, the first lemma is when we let n be an RSA modulus with balanced prime, E equals to n to the power of alpha be a valid public exponent with alpha is between 0 to half, then D be its corresponding private exponent. If the alpha is most significant bits of the private exponents are known, then the constant k in the key equation can be determined up to small constant additive error. And then we prove the lemma by given the alpha most significant bits of the private exponent. We can construct the head such that this condition and D hat is less than n. From 6.3, it follows that this is where we construct k hat, where modulo of epsilon is less than half. And then this satisfies k minus k hat, modulo k minus k hat is less than 9, where we have used this condition into this equation. Therefore, the constant key in the key equation lies in the range of k hat minus 8 until k hat plus 8. Since k hat can be computed in time polynomial in log n, the result follow. Okay, so this first attack by Bonnet, Durfee, and Frankel that we present applies to all public exponents smaller than n to the power of half. Okay, so we use theorem 6.7 where we let n such as the above, and then we let k be the constant in the key equation, and E is equal to gamma multiplied by K for some gamma is greater than 1. Given the 1 minus alpha most significant bits of the private exponents for the modulus n, given the 1 minus alpha most significant bits of the private exponent, the modulus n can be factored in time polynomial log n and gamma. We prove the theorem by this proof. Okay, since alpha is between 0 to half, it follows that the fraction of known bits 1 minus alpha is greater than alpha. And so by lemma 6.6, we can construct k hat such that the constant in the key equation satisfies this condition. And then we assume that we know k, so we can compute dk is equal to e to the power of -1 mod k, since e and k are relatively prime. It follows from the key equation, that dk also satisfies dk equals to d mod k. Thus, we can express the private exponent as this for some unknown d big D. Okay, we can almost completely specify D with D hat over K. And then we notice that the private exponent can be written as this. All right. So, okay, where everything on the right hand side is known except for V. So this is V. Okay. And then since V is equals to E is less than E over K equals to gamma, there are at most 2 gamma plus 1 possible integers value that V can be. So we can compute a candidate for D, and hence the private exponent is this. When V prime is equal to V, we have D prime equals to D, and the private exponent is found. The modulus can be easily factored since Vn is equal to Ed minus 1 over K is revealed. Therefore, when K is known only for this, candidates needs to be tested before the modulus is factored. Since K is not initially known, we can simply repeat the above method, which is with each K prime is in this condition. So that is, we fix V prime equals to 0 and we try each candidate for each value of K prime. Then we fix V prime equals to plus minus 1 and try each candidate for each value of K prime. And we can continue in this way until K prime is equal to K and V prime equals to V, which reveals D and factors the modulus. Okay, so this is the first example from the books. Okay, so firstly, we consider the public key EN, E as 33054 for N, and N is 361152675086. 561000587, and then we were given D hat as this, which is the most significant bits of D, and then we begin by computing K hat equals to self function of E D hat minus 1 equals over N, and then we will get 8979098. We assume that K hat is equal to K. For now, we compute dk equals to this, and we will get dk 156935, and we generate the first candidate for D using D prime using V equals to 2. So we will get this for the first candidate for D. And then we compute phi as in this equation, E D prime minus 1 over K hat and then we will get this. After that, we solve the equation if it's not, if to check whether it is to check whether the modulus can be factored or not. Okay, so if the modulo can be factored, then we know that k hat is equal to k, v prime is equal to v, and d prime is equal to d. So in this example, the public exponent has size alpha equal to 0.3333, and we are given the 0.6763 most significant bits of the private exponent d. Also, the floor function of E minus E over K is 3. Okay, and then we move on to my example. Firstly, we consider the public key En is this. So I choose E is 44387 and N is 2145 679687. So we were given dt, which is this. And then from dt, we compute k1, which is the self function of E multiplied by dt minus 1 over n. And we will get this. Okay, we will get 43227. And then we assume k1 is equal to k. We compute d1 and then we will get this 22247. And then after that, we generate candidates for d, which is dc1. We choose v equals to 0. And then we generate the first candidate for D, and then we will get this for D1. Okay, so from the first candidate for D, we compute phi D1, which is here. Okay, and then we solve it to check whether the modulo can be factored or not. But we cannot obtain the candidate. We cannot obtain the factorization of n. So we have to choose different k prime in k1 minus 8 until k1 plus 8. So we add 1 here. We try to add 1 here to make the new k1 as this 43228. And then we repeat the same method, which is this. We assume new k1 equals to k for now, and then we compute the new d1, which is this. So we will get 8019, and then we generate the new candidates for d using dc1 and v equals to 0, and we will get this 2089563083. We assume v equals to 0, and then we compute phi1, which is phi for dc1, this for the new dc1, and we will get this for phi1. And then we solve phi1 by doing this equation to check whether the n can be factored or not. Luckily, the n can be factored into this factorization. So we will get and then we solve the system. Use the factorization n equals to 46807 multiplied by 45841. Thus, we know that the new k1 is equals to k, the v prime is equals to v, and the new dc1 is equals to d. So in this example, the public exponent has size alpha equals to 0.4980, and we are given the 0.5020 most significant bits of the private exponents. Also, the gamma is 1. So I think that's all from me. Thank you.